Hi everyone. So I'm Rohit Kumar Singh, the teaching assistant for this course, Experimental Physics 2. And today we have an extra session uh, in addition to the 12 weeks session. So for today I would try to try to address your general doubts and any question that you have, and I'll also recap some of the concepts from previous lectures and solve some problem also.
So here, let's start with the first problem. So the first problem that I'm going to discuss is uh, so the question is who gave the quantum theory of light? And so we have the options like Albert Einstein, Heisenberg, Michelson and Morley, and then Max Planck. So as you all might be knowing, Max Planck is the correct answer. So let me tell you some of the history behind the quantum theory of light. So basically, this was given in the 1905, and so the way this quantum theory of light was discovered was, so there was this spectrum, black body radiation spectrum was there, and uh, so from the Rayleigh-Jeans formula, it was expected to go like this. So it is expected to shoot up to infinity at higher frequency, but what was observed was that uh, it it will go up like, and then it will saturate and then come down at the higher frequency. So this is our frequency of light, mu, and this is the spectral energy density, d nu. Okay, so now how so to explain this abnormal behavior, what Planck did was he added a term in the spectral density formula, which contained this h nu by kt term basically, and this h nu is the quanta of energy that a photon has. So he postulated that this much energy a photon has if its frequency is mu. So for a frequency of radiation mu, the energy of each photon will be h mu. Okay, so yeah, that's how this quantum theory of light came into existence. And let me write the formula for energy. So this is the Planck radiation formula. There's some constant factor. H is the Planck constant, and this c is the speed of light, and the mu is the frequency, and then we have this exponential factor. Okay, so this is the Planck radiation formula. Okay, so this was this was the theoretical expectation from Rayleigh-Jeans formula, and this is what Planck gave. Okay, and which explained the black body radiation. Okay, so yeah, that's it. Let's go to the next problem. Uh, here the question is, uh, hydrogen atoms are excited from ground state to the state of principal Compton number 5, and then the maximum number of spectral lines may be observed is. So there in the hydrogen atom we have many energy levels, and here the electron is excited. So hydrogen atom is one electron, and it is excited to the fifth energy level. So 1 2 3 4 5, and whenever some excitation happens, the electrons will de-excite, so it will come down and it will emit some radiation, photons. And so here we and each different transition to different levels will have photons of different frequency, because as I mentioned. So these will contain the quanta h mu, and this energy will depend on the transition levels, like 4 5 to 1. The energy will be different, so frequency will be different. For 5 to 2, so different, like that. Okay, so we have to count the number of spectral lines that will exist here, and so you can see so these two will be there, then there will be a transition from 5 to 4, then from 4 to 3, like this, 4 to 2. So yeah, I mean there will be many transitions. The general formula you can sum it up, and let me write the general formula, and then I'll write the formula for transition to ground state. So basically general formula is given like this. So, okay, yeah, it is so suppose n is your highest orbit, and n is small n is the or last orbit in which the transition is happening, and the formula is a number of spectral lines n minus small n minus n plus 1 by 2. Okay, so if you put n equal to 1 here, because we are asked to calculate the spectral lines from for the transition of 5 to 1. So if you put n equal to 1, the formula will simply become n minus 1 into n, right? So it only depends on the highest orbit, which in our case is n equal to 5. So you can just put n equal to 5 here, and your answer will be, so 5 into 4 by 2, so it will be 10, right? So yeah, it's none of this. Okay, there will be 10 spectral lines, and yeah, so you can count it by hand also if you want. 1 2 3 4 5. So from 5 you will have 5 to 1, 4 to 1, 3 to 1, 2 to 1. Then you can have 5 to 2, 5 to 3, 5 to 4, right? So like this you can count. Okay, so yeah, that is also an easy problem. So let's go to the next problem. here we have the question is the radius of the Bohr orbit depends on which of the following principal quantum number, where n is the principal quantum number. So there are options like 1 by n, 1 by n square, and then n square. So let's try to see how the radius depends on the principal quantum number. For that, let me do a little derivation, and that will show how we can calculate this formula for radius. Okay, so if there is a circular orbit, and classically we can write it, so the centripetal force, we can write it like mv square by r, where r is the radius. So suppose this is the nucleus and electrons are rotating, and this force that which sustain the which make it go round and round, it's called it's the electric force of the nucleus, so it will be simply Coulomb force. And for hydrogen atom, there is one proton inside the nucleus, so it's just E plus, and charge of the proton, and E minus is the charge of the electron, so just E square by R square. And the condition for dynamically stable orbit is just centripetal force is equal to electric force, which we can write it like that, and we can cancel R here, so we'll have the formula for R here, formula for R from here. So radius will be E square by 4 pi E epsilon naught mv square. Okay, and yeah, so now then you also have wait, yeah, and also you can write it like so for the velocity you can write this as E divided by 4 pi epsilon naught. So from here you can write mr. Okay, now and yeah, so this you have. Then what you can do is you have the formula for wavelength, and so basically the electrons that are rotating in around the nucleus, they will have some momentum, and that it's called it's the theory from de Broglie's work, which says that for some momentum you have some wavelength. Okay, so this is simply given by h by mv, the wavelength of the electron in the orbit. Okay, and so in terms of this velocity that we have calculated, the wavelength can be written like this. So we just have to substitute v in here, and you will get h by e under root m, and here 4 pi epsilon naught r, right?
Within this range, photons are absorbed.
And now also there is so for the stability of the orbit, so suppose now we are saying that this electron is a wave.
So how is it related to A
Okay,
moves
and suppose this is the wavelength, and to have a stable orbit, this wavelength should correspond to so this the number of so suppose n waves are there in the orbit, it should be equal to some 2 pi r n. Okay, otherwise you won't have a stable orbit. It should be the so 2 pi r is the circumference, and it should be equal to that, right? uh,
Yes.
so now we can substitute for lambda from here, and let's do that. So what will we get is 2 pi r n is equal to nh by e 4 pi epsilon naught r n by m, right? And now we can calculate this rn. So just square the both sides. Let me do that here. If you square the both sides and take rn on one side, you will get n square h square epsilon naught by pi m e square, where the n is your principal orbit number. So you see this radius is proportional to the n square, and this is how you can simply derive it. So this is not a robust calculation. It assumes some classical things, but essentially it gives the correct proportionality. Okay, so yeah, this is all for this problem. Let me go to the next one. So the fourth question is, what is the energy required to ionize a hydrogen atom from the third excited state if the ground state of hydrogen atom is minus 13.6 electron volt? Okay, so we know that from the Bohr's theory, the energy of nth excited state is given by this formula, right? And so we can substitute the radius rn that we got here, this one here, and what you will get is this. The pi will cancel. So the energy of different orbits are indirectly proportional to n square, the principal quantum number. So the higher in the orbit you will go, the less energy is required to ionize the electron. So, and it's always negative because we have to put the energy back into the hydrogen atom to ionize the electrons, to make it free. So, and this for the if you put everything like mass of the
Yes.
electron and charge of the electron and this Planck constant, the value that you get is minus 13.6 electron volt 1 by n square. Okay, So now the problem at hand is what is the energy required to ionize a hydrogen atom from third excited state, and the ground state energy, as I showed you, is 13.6 electron volt. Okay, because n equal to 1 here, so it is just if you put 1 here, it's minus 13.6 electron volt. Now, and in the problem it's saying, so we have this third excited state, equal to 3. So now, so what we can do is we can calculate the energy required to ionize the atom if the if it's in a third excited state. Hello Poonam. Can you hear me? Hello? Hello, if you can hear me, maybe unmute and let me know. Hello? Okay, I hope you can hear me. So yeah, I was just going through these problems for week 2, and yeah, most of the students didn't join, so I'm recording the lecture, and it will be uploaded on YouTube. So that's why I'm just going through it. Okay, you can stay and ask any question if you have. So let me go through this problem once again. So this question is, what is the energy required to ionize a hydrogen atom from third excited state if ground state energy of hydrogen atom is minus 13.6 electron volt? So I have written this formula for nth excited state energy, ionization energy, and it's just minus 13.6 electron volt into 1 by n square, where n is the nth excited state. So here it's given the third excited state. So what we have to do is we have to calculate what energy required if our electron is in third excited state to ionize it, to make it free. Okay, if it's in the ground state, we need minus 13.6 electron volt, and for third excited state we have to just put here 3, so it will be less than what we need to ionize a ground state hydrogen atom. So minus 13.6 by 9, so the exact value will be something like yeah, minus 0.85. Okay, sorry, minus 0.85, yeah, electron volt. So this much energy you require to ionize a hydrogen atom at third excited state. Okay. And of course the value will report in positive. So yeah, hello Polly Reddy, hello, hi, can you hear me? Can you guys able to hear me? Okay, thank you. Okay, so yeah. Okay, so let me go to the fifth problem. I'll it would be nice if you can mute and uh, interact with me. It will be nice. So since you guys have joined late, I have already solved 4 problems. Okay, and if you want, I can go through them quickly. Just recap it. So do you want me to explain you these 4 problems? Would you like me to explain? They are very easy problems, so I can quickly go through them. Okay, please respond. Yes or no, please respond, or if not, then I can continue from problem 5. Okay, you want me to go through the problems, right? So why don't you guys unmute and say something? Is your mic not working, or some problem is there? Okay, no mic. Okay. Okay, no problem. You can ask anything through the chat. Okay. So, okay, let me go through it. So, uh, I was not there in the previous Saturday session. I was traveling, so I shifted the session to next Monday, that is day after tomorrow. I'll be covering the third week on that day. So today I have the content for second week, and so it basically contains modern physics and some experimental aspects like percentage error and significant digits kind of thing. So yeah, the first problem that I have here is it's a simple question: who gave the quantum theory of light? And you all might know it. So the answer is Max Planck here, uh, who is also known as the father of modern physics. So the way he discovered the quantum theory of light is, so there was this problem in the beginning of 20th century, that the black body radiation spectrum uh, from the Rayleigh-Jeans formula, it should go, uh, so it should be proportional to the square of frequency. So the spectral density u nu d nu, it should be proportional to the frequency squared. So it should shoot to infinity as the frequency increases. Here in this graph you can see. But what was found is that it doesn't go infinity, it saturates at some frequency here and then falls down. sorry. Okay, so to explain it, Max Planck did a guesswork, and he divided the religions formula by a factor which contains exponential of h nu by kt, and this h nu, he postulated that it's the energy of photon, energy of electromagnetic wave of frequency nu. Okay, so he quantized the electromagnetic wave in different quanta, and that quanta he postulated it as photon. And so this is called the Planck radiation formula, and it perfectly fits this observation. So that's how this quantum theory of light emerged. Okay, so any question in this? You can write in the chat or unmute and ask. Okay, thank you. So then the second problem I had is, so this hydrogen atom, when excited from ground state to the state of principal quantum number 5, so you know that there are different excited state in an atom. So n equal to 1 is our ground state, n equal to 2 is first excited state, then third, fourth, and then fifth. Okay, so so suppose the hydrogen atom is in fifth excited state, so the electron is at n equal to 5, and then it's asking that the maximum number of spectral lines that will be observed. So spectral lines are, so when the electron de-excite to a lower level, it will emit some radiation, right? And this is called spectral line. So one transition will correspond to one spectral line. So there will be many transition, right? From here it can go to second level, it can go to third level, then the third level can de-excite to first level. So like this there will be many de-excitation. So the general formula is given by this. So number of spectral lines is given by capital N minus n into capital N minus n plus 1, and the capital N is the highest orbit from where the transition is happening, and the lower orbit is this small n. Okay, and so here it's asked de-excitation to ground state, so we'll take the small n as 1, and with this the formula just become n minus 1 by 2. So if you put 1 here, it will be n minus 1, and this n and 1 cancel, so n minus 1, and so you put n equal to 5 because our excited state is at 5, and you will get the answer as 10. So the option here is none of these. Okay, so any problem in this one? If you have any question, you can ask. Okay. So okay, thank you. Let me go to the next problem. This is a very simple problem. So yeah, here the question was the radius of the Bohr orbit depends on which of the following. So it's from the Bohr's theory of atomic spectra. So the options were 1 by n, 1 by n square, and n square. Okay, so I did a derivation of radius of the Bohr orbit. So the way I did it is, so So suppose, so the simple picture here is you have a nucleus, and here, as you can see, so you have this nucleus here, and then you have electron revolving around the nucleus, and this picture, and so there will be a centripetal force which will depend on the velocity of the electron, which, and it's given by velocity and mass and radius. So it's simply given by mv square by r, you all know. And the force which is generating this centripetal force is this electrostatic force between these two charges. So there, in the nucleus of hydrogen, you have just one proton and you have one electron here. So this is the Coulomb force between these two, and so the stable orbit will be when these two forces balances, and from there you can calculate the radius of the of the orbit, and also the velocity of the orbit by inverting it, okay, in terms of radius and mass and electronic charge. Okay, then from the de Broglie's theory of wave particle duality, we know that the electrons are not really electrons are also behave as a wave when they are in the orbit. So, and the wave will sustain only when so suppose there are n number of wavelengths in the whole orbit, it will be equal to the circumference of the orbit, right? So, and this will change for each different levels. So this radius has an index n here, okay? So when you put that here, and also this the wavelength for a particle of mass m and velocity v, so simply for a particle with momentum p, the wavelength is given by this formula h by mv. So you can put for v from here, from this formula like this, and you can in the place of lambda you can put this 2 pi rn by n, okay? So you get this one, and then you can square both side, and you can calculate the radius in terms of principal quantum number and other variables. So you will see that it's proportional to the n square, okay? So that's how the answer is D. So yeah, it's a little bit there are many steps here, so you need to understand each of them. So yeah, if you have some question in this, you can ask. Is it fine? Okay. So then sorry. Then the fourth problem was simply what is the energy required to ionize a hydrogen atom from a third excited state if the ground state is minus 13.6. So you guys know that the energy for level n is given by this formula, and it's simply proportional to 1 by n square, where n is the number of excited state, I mean nth excited state, and this factor minus 13.6 the electron volt is there. So for the ground state you can simply see that 1 by 1, so it's just minus 13.6 electron volt. So for the third excited state you just put n equal to 3 here, and you will get this value minus 0.85 volt, okay? So 85 electron volt, And so the energy required is simply simply 0.885 electron volt. So this negative sign is just so that you have to give the energy back to this system. It's a convention, okay, and the energy that you have to give is 0.85 electron volt to make it free. Okay, so it's also a simple problem, you all must know it. So yeah, any question here? It may be 1.51.
Okay, because most of the
Okay, let me
most of the
see.
atoms are already
Have
has
I
come to
written?
the ground state.
So
But
third
first
excited state, right?
quantity is in ground state.
Sorry. No, not by 3. So yeah, first excited state is n equal to 2, second is n equal to 3, third is n equal to 4. Oh, sorry, my bad. So we have to divide by 4 square. 16. Sorry. Yeah, I mean, I remember the different, So it's, yeah, anyway, it's 0.85. Thank you for the correction. Okay.
Yes.
Yeah. Yeah, sure. Thank you. Okay. So
Okay,
let's,
so
now we have this. So here I was, fifth problem.
yes, understood. Yeah.
So here
Okay, I understood this.
the question is the percentage errors in the measurement of mass and speed are 2 and 3%. Okay, and how much will be the maximum error in the estimation of kinetic energy obtained by measuring mass and speed? Okay, so the kinetic energy is simply 1 by 2 mv square, right? And so last time I did the derivation for error calculation. I mean the last session, if you guys were there, you can answer it just by looking at the formula. I showed you a trick also, but yeah, let me know, can you answer it, or do I have to do the calculation? So the options are 11%, 8%, 5%, 1%. So which of these do you think is right? Should it be simply the addition of these two, 2 and 3%, which is 5%, or will there be something else? Is it true? If it were only MV, obviously it will be just 5%. But since this square is there, it will change, right? So let me do this. Okay, so maybe 8. Yeah, you're right. So the percentage error is given by this, right? And here, so the half doesn't concern us, it's just a constant. And I showed, in the derivation I showed that when there is a multiplication, it will go into a addition because we take the log on the both sides. So dm by m into 100, and this square will be multiplied here, and dv by dv will be there in 100. Okay, so this is given as 2%, and then you have 2 into this is given 3%. So yeah, you are right, it's just 8%. Simple. Do you want me to derive this formula, or you know this? Okay, thank you. So yeah, this is very simple. Then we have another problem here. So it's a very simple thing. The unit of percentage error is, so there are four options. So which of these you think? Unitless? Why? Why do you think it's unit? So percentage error. Percentage error is given by so suppose P is your quantity, then it's given by dP by d by 100 into 100, right? Like I showed here. So whatever the unit of P is, yeah, the ratio of same quantity. So it will cancel out and it's unitless. Simple thing, just wanted to remind you. Okay, then next problem we have. So the magnitude, yeah, it's also a simple reminder. So just answer it.
Yes, yes.
The difference between individual and true value is what it's called. Absolute error, relative error, zero error, percentage error. It's easy, right? So can you answer what it's called? You have some true value and your measured value. Okay, so it's simply, yeah, it's the absolute error. Percentage error, you know, relative error is, so relative error is P true minus P measured divided by P true. So relative to, so this is a relative error which sometimes is more helpful. And then zero error, you know that, so for the different measuring devices you might have some zero error. I explained that in the last session. So okay, I hope they are all clear. Okay. So then the 8th question. A physical quantity X is expressed as this, and the percentage error in measurement of A, B, C, and D are 1, 2, 3, and 2%. So what is the maximum percentage error in X? Okay. It's also a simple problem, so let me write the formula first. So this is the percentage error in X. Then you have A into B half, B to the power half. So so the multiplication and division will be represented as addition here. So yeah, so it will be just dA by A plus, so half will come down, dB by B plus 1 by 3 will come down, dC by C plus 2 dd by D, and whole into 100. Okay, so this is the percentage error in X, and we are given all the percentage errors. So dA by A into 100 is 1 plus half into 2 plus 1 by 3 into 3 plus 2 into 2, so it's 7%, right? A simple problem. So these things are very trivial. You all should be able to do this. Any question in here? Thank you. Okay, the next problem I have is, so the sides of a rectangle are given, and we have to write the result of the area of the rectangle in appropriate significant figure. So do you know the concept of significant figures? So the sides are given as 4.215 and 2.08 centimeter. So how many significant figures are here and here? Can you please tell me in these two numbers? Here 2 and here. Okay. So you're saying here it's 3, here it's 2. Is that so? Okay, so maybe okay. How do you like, okay, yeah, the answer is correct, 8.77. But why is that? Can you tell me? Okay, let me answer it. So area is simply, significant figures are 3. Yeah, but here the significant figure is 4 and here it's 3. So when you are calculating something, so area L into B, so you are multiplying and you will get this 8.76 and 7672, something like this. But you cannot report it like this, okay, because initially you have precision only up to here 2 digit after the decimal, okay, and I mean, so what it means that you have only 3 significant digits, so you cannot report it like this. So you can only report it up to 2 digit after decimal, so that you have total 3 significant digits, okay. So that is the rule. So in exam, yeah, I think calculator should be there. Virtual calculator will be there. Okay, so yeah, this is also easy problem. Just to refresh the concepts of significant figures.
Yes, all the elements are not useful.
Okay. And yeah, so sorry, so we have to we cannot write it like 8.7. We can round it actually, so 8.77 will be the answer. I wrote it wrong because we have to report it only up to the 2 digit after the decimal, so we can round it off and report it like this. Yeah, that's the thing. Okay, now the question is, a car covers a distance this much to 2458 0.56 in 121 seconds. Okay, what is the speed of car? So now how will you report it? So the speed is simply distance divided by time, okay, and this will give you so what will be the exact answer? 20.31867769. If you calculate it using a calculator, this type of answer you will get. But can you report it like this? No, right? How can you report it? How will you report it? Using the significant figures. So you have to see what is the least significant figure. No, you are wrong. Because here the least significant figure is 3. So in the answer we only can report it, we have to round it to 3 significant figures. Okay, so we can report it only like this, 20.3. Okay, so that's the concept. You have to see what is the least significant figure here in the calculation is. Okay, so now this is also a simple problem. Now the last problem, this one you should be able to tell me correctly. Okay. The sides of cuboid, what do you say it, is given. So 2.3 centimeter, 2.35 centimeter, then 4.245 centimeter, and 1.142. These are the dimensions of a cuboid. The volume is simply length, breadth, height. So you multiply all these. Okay, do it. You can do it in your calculator and tell me the answer. And then I'll ask how will you report it? Okay, so the volume what you will get from calculator is something like this. Okay, now how will you report it? 11.4 you say. Okay, why? What is the least significant figure here in these 3 numbers? It is 3, right? Yeah. So yeah, you can only report it up to 3 significant figures, so we'll have to round it. So rounding it will give us 11.4, right, centimeter cube. So yeah, this is the correct answer. Okay. So yeah, this is the last problem that we have. So you want to ask anything, or we have much more time, so maybe if you want to discuss anything you can do. Hello, Polly Reddy. Do you have any question? Anything you can ask?
Yes, but that about this how.
So yeah, my research area is high energy physics. So I'm working in collaboration with CMS experiment at CERN, and I study heavy ion collisions. So collision of 2 nucleus, suppose lead nucleus, and after that there is a state that get produced called quark-gluon plasma. So do you know what quark-gluon plasma is? Okay, so you know what simple plasma is, like normal the plasma state of matter. Yeah, fourth state. So what happens in plasma is you apply some magnetic field or electric field in a gas, and you ionize the electrons, so you have freely moving electrons and ions. Okay, so that you called a plasma. So in the same way, so neutrons and protons contains these quarks and gluons. So quarks is the fundamental state of matter, okay, and gluons are the so force mediator between the quarks. So gluons are mainly which uh, bind together the neutrons and protons. Uh, okay, and when you collide the two nucleus at very high energy, so the energy of collision is 5 teraelectron volt per nucleon. And so in the nucleus, so in the lead nucleus you have 240 neutrons and protons around, so you can imagine how much energy is there. So what it does is it deposits that much of energy that the quarks and gluons get ionized, and they move freely in that nuclear volume, okay, free from this uh, proton and neutron proton and neutrons which confine them. Okay, so that we call the quark gluon plasma. So there you have freely moving quarks and gluons, okay, outside the neutrons and protons. So it's a very exotic state of matter. It exists in the neutron stars, in the core of the neutron stars, and yeah, we are able to produce it here in our lab with heavy ion collisions. So yeah, basically my work is related to that. Anything else you want to ask? So let me ask you, what are you studying right now? Like which year of bachelor's or master's you are? And your college? Can you hear me? Okay, you are a lecturer in physics. Okay, wow, that's nice. So, so yeah, these things must be very simple for you. So, but yeah, maybe in the later weeks there will be some advanced stuff. Uh, and please try to have a system with mic on, so that we can talk and interact more. Okay, so what do you teach, like mainly what do you like to teach? So you have completed PhD in glass science. Okay, nice. So what is I mean, glass science, what do you do in glass science mainly? Okay, structural properties and of glass. Okay, that's nice. So yeah, I mean, how will this course help you? Like, do you think this course will help you? Because it's meant for first year undergrad students mainly. Okay, yeah, I mean, if you want, we can talk about research also. I mean, I'm not involved in So yours is on mainly material science, as far as I can understand. Yeah, but we can talk about it more if you have. Oh, you are in engineer, working in engineering college. Okay. But your PhD in a physics, your PhD is in physics, right? Or some engineering. So glass science is a part of physics or engineering?